thanks to Blinkist for helping support this episode. Must animate more clones! Wait, is this even gonna work? This episode was made possible by generous supporters on Patreon. Hey crazies, let's have some fun and apply what we know about electrodynamics to the nervous system. Brains! It's a field of study called electrophysiology, which mainly covers nerves, but is also concerned with things like muscles and the heart. 'Cause you know, that nervous system thing is all over the place. Electrophysiology shares some important history with electromagnetism and physics. To the timeline! Prior to the late 18th century, models for mechanisms underlying the brain and movement involved various types of fluids and spirits. In ancient Greece, fluidy, spirity stuff was referred to as pneuma. But that word has since become a prefix for other words, like pneumatic and pneumonia, which are related to gases and pressure. In 1646, René Descartes argued that the neuromuscular system was essentially a hydraulic system, where animal spirits flowed from parts of the brain into the muscles. But by the 1790s, we started to figure out what was really going on. In 1786, Luigi Galvani entered the field of physiology. It's me, Luigi! No, not that Luigi! Unbelievable. In 1786, Galvani did a few experiments with lightning rods and frog legs. They were dead frog legs. There was no animal cruelty going on here, okay? Anyway, he hooked up a lightning rod to some dead frog legs, and they twitched in response to electric shocks. Galvani called this behavior animal electricity when he finally published it in 1791, in an essay called Commentary on the Effect of Electricity on Muscular Motion. You know, a typical boring science title, but descriptive. Eventually, Galvani discovered the lightning rod wasn't actually necessary. He could make the dead frog legs twitch simply by touching them with a combination of two metals, called a bimetal. Galvani used this fact to argue that animal electricity was actually intrinsic to the frog itself. And as we'll see soon, he wasn't completely wrong. But a rival of Galvani's named Alessandro Volta argued that— Wait, Volta? The Volta? The Volta we named the Volt after? Yep, that's the one. Volta suggested that animal electricity wasn't intrinsic to the frog, but came from the bimetal somehow. And as it turns out, Volta was right. The bimetal is capable of producing its own electricity. The two metals reacted with the electrochemical fluids in the dead frog leg, forming a primitive voltaic cell. Huh? A battery. The bimetal turned the frog legs into a battery. Really? Yes, really. Volta literally discovered electrochemistry and invented the precursor to the battery just to prove Galvani wrong. It's crazy where an argument will take you. Anyway, back to the timeline. Voltaic cells set the stage for experimental physicists like Ørsted, Ampere, and Faraday to develop electromagnetism in the 19th century. So the next time you charge your phone, don't forget about the frog. Galvani stopped his research after Napoleon invaded Italy in 1796. But the idea of reanimating life with electricity captivated early 19th century society. It was the inspiration for Mary Shelley's Frankenstein in 1818. So, is this gonna work? Nope, definitely not. Frankenstein is just a story. This is not how clones are made. Okay then. Luigi Galvani was probably stimulating the frog's sciatic nerve. A nerve is a biological cable consisting of a bundle of fibers called axons. What's an axon? The part of a typical neuron that carries electrical impulses. When it comes to the brain, the neuron is usually the star of the show. Your brain contains about 100 billion of them. Isn't that also the number of stars in the Milky Way galaxy? Yeah, it's the right order of magnitude, but why are you asking? Didn't you say it was the star of the show? Yes, as a metaphor. This video is about brain stuff. So what's a neuron? A simple model of a neuron has three parts. The main cell body, dendrites, which receive signals, and axons, which send signals, and can sometimes span an entire limb. One of the things that makes neurons special is their ability to generate and transmit electrical pulses over relatively long distances. And they do that reliably and fast enough to respond to the environment. So Galvani was on the right track? Kind of, but we've come a long way in our understanding of electrodynamics since then. Back to the timeline. We'd have to wait until the 20th century before scientists really pinned down the biophysics of this electrical axon thing. In 1906, Ramon E. Cajal received the Nobel Prize for his pioneering work on the general structure and function of the neuron. But it wasn't until 1952 that Alan Hodgkin and Andrew Huxley teamed up to discover the biophysical mechanism for electrical pulses in neurons. Hodgkin and Huxley were both biophysicists, so they decided to tackle the problem. And they did their experiments on the squid giant axon. A giant squid axon? Like 20,000 Leagues Under the Sea kind of giant squid? No, not a giant squid axon, a squid giant axon. The axon was giant, not the squid. That made it more accessible and easier to work with. I mean, who wants to work with a tiny human neuron, am I right? Anyway, if you look up the Hodgkin-Huxley model, you'll probably see differential equations that look like this. Of course, equations don't exude intuition, so let's try to make a visual instead. Think of a neuron like a leaky bag of charged liquid. It's mostly water, but it has ions like potassium, sodium, and chlorine dissolved in it. A neuron, like all cells, has a two-layered cell membrane. When it's not doing anything, the neuron maintains a potential difference, a voltage, across the membrane. How does it do that? Ion pumps. Ion pumps run on chemical energy known in the bio world as ATP. This is a major reason our brains consume 20% of the energy we eat. Outside the cell, there's a higher concentration of positive ions like sodium. Inside the cell, there's a higher concentration of positive ions like potassium. Negative ions like chlorine are spread out all over the place. The ion pumps are specialized protein structures embedded in the cell membrane that pump specific ions against the concentration gradient and against the electric potential, if necessary.
Fight the gradient!
I know, this is all sounding very biological, but it's just electrodynamics. It's just circuit stuff. Ion pumps use energy to move electric charges around. That's what batteries and other voltage sources do. In the Hodgkin-Huxley model, ion pumps are like batteries. Remember how the cell membrane has two layers? Well, that's just a capacitor. The ion pumps built up electric charge on either side, creating a voltage. In the Hodgkin-Huxley model, the cell membrane is a capacitor. Ion pumps are not the only devices that span the cell membrane, though. There are also ion channels. When these channels are open, ions can and will try to balance their concentration.
All hail the gradient!
Ions are just electric charges, and when charges flow, we call that an electric current. It's positive charge too, so the idea of conventional current isn't even a lie this time. But what really matters here is what the ion channels represent in the circuit. The ions don't flow through the channels all the time, and they flow at different rates at different times. That's a lot like a variable resistor, one controlled by some kind of timer. In the Hodgkin-Huxley model, ion channels are variable resistors. They control the electric current by Ohm's law, just like any other resistor. Each ion channel is selective though. It'll only allow a specific type of ion to pass through. Sodium channels only let through sodium ions. Potassium channels only let through potassium ions. So how are they variable? Because they're voltage gated. There are actually several different ways an ion channel could be gated. Chemically gated channels on cells that neurons talk to, mechanically gated channels that are sensitive to pressure or stretch, and even light gated channels in the eye. But the ones in the axon are voltage gated. How open they are depends on the voltage across the cell membrane, and that voltage can change with time. In fact, it will change with time as long as that neuron is trying to talk to other cells. These voltage-gated ion channels are vital for getting a signal to the end of the axon. The signal kind of rolls its way down the chain. Hodgkin and Huxley modeled this process as a simple electric circuit. The cell membrane is a capacitor. The ion pumps are rechargeable batteries. And the ion channels are variable resistors. Let's take a look at the voltage across the cell membrane, aka the capacitor, as the neuro tries to send a signal. There are 4 stages: resting, depolarization, repolarization, and hyperpolarization. Jargon alert, jargon alert. I've been dropping bio words this entire video. Now is the time you get on my case? Okay. I suppose technically the membrane is polarized as long as there's a voltage across it. Which, as you can see, is true almost the entire time. It blows right past 0, twice. But we have to tell these stages apart. So it helps to think of polarization as just the resting state. The membrane is stable. Depolarization is when the voltage rises towards 0, but overshoots. Repolarization is when the voltage rebounds and drops toward the resting state. Hyperpolarization is when that overshoots. Don't get too hung up on the names. Wasn't this supposed to be about circuits? Oh, yeah, right. We were talking about the Hodgkin-Huxley model. But I think this will make the most sense if we look at everything together. Let's sync up all 3 visuals. First, the voltage-gated sodium channels are triggered to open, allowing a rapid flow of sodium ions into the cell. The voltage across the membrane goes from -70 millivolts up to around +30 millivolts. But remember, they're on a timer, so after the initial spike, the sodium channels close. When those close, the potassium channels open, rapidly sending potassium ions out of the cell. The voltage across the membrane drops back down toward the resting state. Finally, after an overshoot, the potassium channels close, and the membrane settles back into the resting state. It does this by leaking a little, and if necessary, by turning on the ion pumps. In short, the channels balance the ion concentration, and the pumps unbalance them again. The Hodgkin-Huxley circuit successfully models this entire mechanism, but only for a little patch of the cell membrane. This patch only has a few things: 1 sodium-potassium pump, 1 potassium channel, 1 sodium channel, and whatever other miscellaneous devices are around. The signal process starts locally, usually around where the cell body and the axon meet. It then spreads as a chain reaction from one patch of the membrane to the next. Local regions depolarize their neighbors, sending a pulse down the axon. And this happens fast. Fast! The entire spiking process starts and finishes in about 1,000th of a second. But how fast does the signal take to get down the axon? Good question. It actually depends. It varies a lot depending on the type of neuron and the animal species. But at top speed, we're looking at about 224 miles per hour, or 100 meters per second. That's the length of an entire football field, including the end zones, in a single second. Compared to how fast signals travel through wires though, this is actually pretty slow. Oh no, does that give robots the advantage? Anyway, so it took us a while to figure out neurons. The real work began with Luigi Galvani and dead frog legs, but culminated with Alan Hodgkin and Andrew Huxley and their circuit model. A neuron is like a simple electric circuit, or at least a chain of simple circuits. It's made of capacitors, batteries, and resistors that obey Ohm's law. Components that create a pulsing voltage, all just to tell other cells what to do. Let's just hang here for a bit and take it all in. So, got any questions about this analogy? Please ask in the comments. Thanks for liking and sharing this video. Don't forget to subscribe if you'd like to keep up with us. And until next time, remember, it's okay to be a little crazy. I'd like to thank this video's sponsor, Blinkist. Have you ever been in one of those social situations where everyone's talking about some popular nonfiction book, but you haven't read it? I mean, who has time to read a book in this fast-paced world we live in anyway? I've got more important things to do. Well, Blinkist can solve your problem. It's an app you can get on your phone or tablet. The phone
phone doesn't even have a SIM card.
It's fine. I use an old phone for podcasts and stuff, okay? Anyway, Blinkist takes the best insights from over 3,000 nonfiction books and condenses them into about 15 minutes. You can read the summaries yourself, or even listen to someone else read them to you. They've got books all over the spectrum, like Born a Crime by Trevor Noah, or A Brief History of Time by Stephen Hawking, all condensed into about 15 minutes. They've even started offering member discounts on full-length audiobooks, if you're into that sort of thing. The first 100 people who go to Blinkist.com/Science Asylum can get unlimited access for a whole week to try it out for free. If you don't like it, you can cancel any time during that week. But if you decide to keep it, you'll also get 25% off the full membership price at the end of the 1-week trial. Go to Blinkist.com/Science Asylum, or click the link in the description below to get started. The featured comment comes from Derek Cochran, who said, "Relativity is definitely not a cinch to understand." Ha, I see what you did there. Cinch, as in hyperbolic sign. Good one. Anyway, thanks for watching.